First, we're going to talk about alpha radiation. So let's think about that uranium-238 once more. Remember, the atomic mass, 238, tells us the total number of protons and neutrons, and its atomic number, 92, tells us the total number of protons. I'm going to make a duplicate of this nucleus, and now it's going to undergo radioactive decay. This is an alpha decay. Notice what's come out of my nucleus. I've lost 2 protons and 2 neutrons. That means I've essentially lost a helium nucleus. Now, look close.
Just a second, just so that you see the symbolism here for this decay reaction that's happening. So on the left side of this arrow, this is your starting material. So this is the nucleus for uranium, but we just write it in nuclear symbol form, okay? So this is what you're starting with. This arrow is kind of like the equal sign in math, okay? But we draw an arrow because it shows what is forming. When uranium undergoes decay, it gives off an alpha particle, which is represented by this symbolism, but there's also another symbolism we'll talk about in a minute, and some other resulting product. Okay, and we're going to talk about how to get to that product. And it's actually going to show you the math real quickly here, but we'll go over it more.
Closely at the atomic numbers and atomic masses of all of the parties that are involved here. Notice that the atomic number of uranium-92 is equal to the sum of the 2 products, right? Thorium and an alpha particle. Notice the atomic masses as well add up, right? So charge is balanced and mass is balanced as well. So in this case, I've lost a helium nucleus. That's 4 total nucleons and 2 protons, meaning I have a very massive, positively charged particle being irradiated from that nucleus. And it's giving me a new atom, a thorium-234, to work with for the next step in my radioactive decay. 90 proton means its ratio of protons to neutrons has changed as a result of the emission of an alpha particle, and thorium will seek out to fix that. In order to do that, it has to get more protons per neutron. Now, how is that possible? Well, think again about that equation that we derived earlier, in which a proton plus an electron essentially equaled a neutron. Well, that means that thorium could actually convert one of its neutrons into a proton if it releases a high energy electron known as a beta particle. Now look carefully at our equation here. Our beta particle has essentially no mass and a negative charge, and therefore we create a new element called protactinium. This is the second step in the decay of uranium. A thorium nucleus loses a beta particle in an attempt to recover the neutron to proton ratio that it once enjoyed when it was uranium-238.
Okay, now it doesn't go into the math here again, but we will go into this more. But again, the left side of the arrow has to equal what's on the right. So you can see 234 equals 234 plus 0. And down here, 90 equals 91 plus -1. So that math's a little weird, but because this is negative, you need an extra proton down here to go to 90. The symbolism they used in this video for the alpha and beta particles is actually different than the symbolism I'm going to ask you to use. And the reason is because your test is going to be in Classkick, and you won't be able to type in this Greek symbol beta or the Greek symbol alpha. So for your alpha particle, instead of this, you're going to use the representation where it is helium with the 4-2. Okay, so that was one of the possibilities for your alpha particle. So this is the one you're going to use for your alpha. And instead of using the 0, -1 with the beta, we're going to represent that with the symbol E, because it's essentially just an electron. Okay, so this is going to be your beta particle. So do not use the alpha and the beta symbols just because you can't type those into Classkick. And I'll have you do a little bit of practice in Classkick so you know what I'm looking for. Okay, so now we're going to go into some more of the actual math practice. Again, you can see though that it is not difficult math.
Let's look at three types of radioactive decay, and we'll start with alpha decay. So in alpha decay, an alpha particle is ejected from an unstable nucleus. And so here's our unstable nucleus, so uranium-238. An alpha particle has the same composition as a helium nucleus. So we saw the helium nucleus in the previous video, right? There are 2 protons in the helium nucleus and 2 neutrons. So I go ahead and draw on my 2 neutrons here. Since there are 2 protons, the charge of an alpha particle is 2+. So for representing an alpha particle in our nuclear equation, since an alpha particle has the same composition as a helium nucleus, we put an He in here. Right, and it has 2 positive charges, so we put a 2 down here, and then a total of 4 nucleons, so we put a 4 here. Trying to figure out the other product.
Okay, so anytime you have alpha decay, one of your 2 products will always be this He42. Okay, so if you're given the starting material, you can always figure out one of your 2 products in alpha decay. Then you use that to figure out your missing information. So we're trying to figure out this piece right here. If we do the math that we did before, we know that this equal sign is essential, or this arrow is essentially an equal sign. We know that
from our nuclear equation, I know nucleons are conserved, right? So if I have 230,
we know that 238 has to equal 4 plus whatever number this is up here. So 238 minus 4 tells us that this top number is going to be 234. Now we figure out the bottom number. 92 equals 2 plus whatever this number is. So 92 minus 2 gives us 90. Now this part is important because we have numbers, but we don't have an element symbol. The way you figure out your element symbol is by looking at the atomic number. Remember, the bottom number tells you the atom. 92 is the atomic number for uranium. If we look up 90 on the periodic table, it's way down at the bottom. A lot of what you work on here in this chapter is going to be down at the bottom of your periodic table. It is thorium. My camera's backwards, sorry. But it is thorium. So you would write the symbol TH here. Again, this number tells you what that symbol will be. Okay, so that is the full equation for alpha decay. I'm going to move forward here and skip to a beta example.
-1 charge, you put a -1 down here, right? And let's look at 3 on the left number here. So usually equal to here, 2 and then here, right? It's not a proton nor is it a neutron, so we put a 0 here. So here's our electron. And an electron ejected from the nucleus is called a beta particle. And so we could put a beta here, right? And it's an electron, so a -1 charge, and then a 0 here. So if a beta particle is ejected from the nucleus of a thorium-234, right? So we're starting with thorium-234. This nucleus ejects a beta particle. So we go ahead and put a beta particle in here, so 0 and -1. What else is produced here?
Okay, so again, if we have beta decay, instead of an alpha particle going here, which would be your helium atom, this is going to be a beta. Again, we're going to use an E and not a beta. But whenever you see beta decay, you know that this will be one of your products. And then we do the math again to figure out the missing piece. So 234 equals 0 plus 234. 90 equals -1 plus what? Okay, so this is negative. So that means that we take 90 minus -1. So we need a 91 here. 91 minus 1 equals 90. We look up 91 on the periodic table. 91 is called protactinium. It's down here at the bottom, and it's got a symbol of Pa. And that would be your beta decay reaction. Okay, any questions on the math involved there? All right. Going to do 2 quick sample problems, and then we're going to just do one of the ones below it.
What else do we make? Well, once again,
all right, so you have 2 examples here under balancing alpha and beta decay. This time it gives you more pieces, and you just have to fill in the missing piece and then determine the decay type. So we start with radon, and it shows that is breaking down into this PO plus something else. So all we need to do is the math. 222, instead of an arrow, we're going to put an equal sign in there, equals 218 plus, well, 222 minus 218 is 4. 86 equals 84 plus 2. 2 atomic number on the periodic table is He. So here you have that alpha particle. So that is what tells you the decay type. Whatever, if you have an alpha particle on the right side here, then it's going to be alpha. And if you have a beta, then it would be a beta decay. So that's an alpha. This example, same thing. We have to fill in the missing piece. 228 equals 228 plus 0. Okay, those 2 add up. 90 equals 91 plus, well, to get from 91 to 90, we need to add a -1. And a -1 on the bottom always means we're going to have that electron. And because this particle was one of the products, this is a beta decay. So you just write beta. All right, any questions about that, the basics there? Okay. One of your things that you're going to do for homework is these remaining 4, but I do want to quickly talk about what happens when you're not given an actual equation, but you're just given words. How do you begin setting that up? So after I talk about this, if you need a little more help, you can watch this YouTube video, but let's just talk about how to start this process. So first of all, it just says uranium-238 undergoes alpha decay. We know that we need to make it look something like this, where we have something on the left, an arrow, and then a couple things on the right. So to do that, we need to first figure out what we're starting with. In this case, the particle that is undergoing decay is uranium-238. But that is not written in nuclear symbol notation. So we have to start by changing that into that nuclear symbol notation. We need the element symbol, which is U. This 238 in this what's called isotope notation is the same as the mass. So this mass number is what goes up top. And then we are not given this bottom number, but remember that the bottom number matches the element symbol's atomic number. So we find uranium down at the bottom, and we see that uranium has a mass of 90, or an atomic number of 92. So we can fill that in. We only have one thing that we start with, and it decays. So that means it's going to break down. We're going to draw that arrow to show what it forms. It says it is undergoing alpha decay. So that tells us that one of the products, one of the things on the right side has to be the helium atom. So I'm going to put helium as my first product. It doesn't matter if you put that one first or second. Okay, these two could be switched. Now we need to figure out our missing piece. 238 equals 4 plus 234. 92 equals 2 plus 90. Again, we don't have an element symbol, but this 90 is the atomic number for thorium. Sorry, it's backwards. So we're going to write thorium here. And that is the full alpha decay equation. Those equal signs don't have to be there. I just put them in. That is your full alpha decay equation for uranium-238. Okay, there's a couple of beta decay examples here as well. Instead of the alpha particle, you're just going to have a beta particle to get started. All right. Your job then for homework is to do these 4 at the top of that page and then the remaining 3 here. So you should finish part 3 and then we will start part 4 tomorrow.